Hello everyone, welcome to our seminar of the Particle and Astroparticle Physics channel. Today we have Folkert Kuipers from the University of Sussex. Folkert got his PhD, his bachelor and master in physics and mathematics at the Utrecht University, and he is a PhD student at the University of Sussex. His research area is quantum gravity, quantum field theory, general relativity, black holes, and stochastic mechanics, with emphasis on the application of effective field theory methods to quantum gravity and on the predictions to black hole physics. So he's going to talk about his recent paper, bounds on very weakly interacting ultralight scalar and pseudoscalar dark matter from quantum gravity. Thank you again, Folkert, for accepting our invitation. It's a pleasure to have you here. Please take your time.
Yeah, thank you, Clarissa, and thanks a lot for the nice introduction, for the invitation. Of course, I would have loved to have visited Brazil, but maybe some point in the future this will still be possible. It's very nice that I can give this on a virtual seminar now. So I shortened the title a bit for the talk to make it fit the slide. So it will be on bounds on dark matter masses from quantum gravity. And it will be on work I did in collaboration with my PhD supervisor at the University of Sussex, Xavier Calmet. And I will mostly talk about this first paper, which with the archive number. So this is indeed about lower bounds on the masses for ultralight, scalar, and pseudoscalar dark matter. And then I'll say a few words about this more recent paper where we put together the results with some other bounds and mainly upper bounds. So let me start off. I will start talking about dark matter. This is a field I only recently got into, so I'll give a quick overview of the questions I would like to tackle here. Then I'll talk a bit about quantum gravity, and the main focus will be on what can quantum gravity tell us about dark matter? Is there something we can actually learn from quantum gravity, even though we don't have a UV complete theory yet? And as I promised, then I'll talk about the lower bounds we can set on quantum gravity, continue with the upper bounds, and finally I'll conclude. So let me start with the nature of dark matter. So what do we know about dark matter? Well, there's not much we know about dark matter, but we do know that about like 80% of all matter is dark, meaning non-luminous. It's not standard model-like, most probably. The estimates are a bit variable, so it could be somewhere between 75–85%. And there's quite a lot of evidence for this. And I think one of the famous evidences given usually is the rotation curve of galaxies. So that's why I plot this one. But there's many other kinds of evidence for the existence of dark matter, all coming from cosmological data. So here, for example, in the rotation curve, we see that there's an expected velocity distribution. The further away you go, you expect it to fall down, but the observations differ, so there must be something else. But as I said, we don't know much more about dark matter than that there must be dark matter. So let me try to, so the question is, what is actually this dark matter? Then we could try to answer it and come up with possibilities. The first possibility would be it's something like a fundamental particle. It's standard model-like, but it's not what's in the standard model already. A second option would be to modify gravity. In the end, all the evidence we have for dark matter is gravitational evidence, cosmological, so we use general relativity for that. Maybe we need to adapt general relativity to understand dark matter. Of course, a third option would be that we don't need anything at all, and we can go for the machos, such as primordial black holes, very massive objects that we just don't see well, but they could be there. And then I would like to complete this list with something completely different. I think we should never exclude the option that we just get it wrong and it's completely different. But for this, we really have to wait until, every now and then someone publishes an idea, and then we can actually test it. And until we have such an idea, we cannot do much. So this is not a very specific, and we cannot do much research along those lines. So let us therefore stick with the options I mentioned earlier. Yeah, so let me go to machos, and this is actually very clean because we don't need any new physics to explain dark matter. It's just all standard model and general relativity. As I said, very massive objects, maybe brown stars or black holes. Maybe we just don't estimate the amount well enough, but unfortunately, it can only account for about 1%, and there are some ways to get around this 1% maybe, but I think everyone is pretty convinced that there's no way to account for all the dark matter density using machos. It will only be like a very small amount, and this has been known actually since 2000 in this paper. And the same actually goes for, of course, in standard model, there's also another candidate, which are the neutrinos, and they will also maximally account for about 1%. So in the end, there will always be like 75% of the matter we don't understand, and we need to do something for that. All right, so then let me go to the modification of gravity, which is of course very appealing because, as I said, the evidence for dark matter is all cosmological. But the thing with modifying gravity is it's quite difficult to get a model that satisfies our experimental constraints and still remains predictive. Of course, if we have a model, we want also to make new predictions such that we can actually say something about dark matter. And one of the main evidence used against modification of gravity is the famous picture of the bullet cluster. And what we see here is basically in blue, we see the center of mass for dark matter, and in red, the center of mass for luminous matter after a collision of two galaxies. And what we see is that there is a difference in these locations of the center of mass. So that means that if we are going to modify gravity, then all the mass must be located at where we see it. And gravity should be something non-local, right? Because of the fact that these clouds are clearly distinguishable. And there's actually a second thing, which I will come back to in a couple of slides, that we can learn from this bullet cluster, and that's that dark matter got away further apart than the luminous matter, which means that the dark matter is also not very much interacting with it in itself. Otherwise, it would have slowed down more. So this is why I would propose to go and look at particle dark matter today, at least. And there's a second reason why I think particle dark matter is nice to look at, and that is even if the answer would be modification of gravity, then it is possible that the modification of gravity is actually the second side of the same coin with adding a particle to our standard model. So we know, for example, for an f of r theory, which is a modification of gravity, that we can do a conformal transformation and map it to a theory with an additional scalar field. Of course, we have to be careful here that this mapping is bijective, so there are some things you have to be careful about. But in general, there are sometimes bijections between modified gravity theory and particle dark matter. So even if it would be modified dark matter, then we would still modified gravity, then we would still be able to see it as its particle behavior. So let us go to particle dark matter. That's what I want to talk about today, and try to see if we can set bounds on the masses of such particles. So the idea is very simple. We have the standard model, and there will be a hidden sector with other particles, and there might be some portals. This might be like standard gauge portals, but we don't know about this. The only thing we know is that there's some gravitational portal, and I kind of like this picture when I found it a couple of days ago. It suggests kind of a wormhole. So this is where the quantum gravity will come in later today. But of course, we have to ask some questions about this dark matter. And the two fundamental questions we always want to ask if we want to know a particle is, what's the mass of the particle? And, well, this is the first one. And we don't know much about the mass. I'll get back to the bounds soon, but in general, the only strong bounds we have is that it's somewhere between 10⁻22 and 10 to the 70 eV. And this is what I would like to tie down a bit, at least by order of magnitude estimates. The second thing we could ask is the spin. This is the second question that will define our particle. And again, we don't know much about this, except for spin is always positive, it's integer, it's half integer. And that's about it. Of course, we would expect that it will be a low spin, as that is what we're used to in a standard model. So that's why I will today focus on scalar dark matter mostly. I will talk a bit about fermions, spin half, fermions, and vector boson spin 1, and also say something about spin 2 particles. But of course, in order to answer these fundamental questions, and actually once we have answered these fundamental questions, we want to ask further questions. So we would like to know, are there interactions with the standard model? Is there something more than gravity? And that could help us to answer these questions. But of course, once we've answered these questions, it will also be important for applications to know about these interactions. And again, all we can say is, well, we have never detected in dark matter in our experiments. Moreover, there is, quite a lot of dark matter. There's quite a lot of ordinary matter. So it's not expected that there will be very strong interactions. Otherwise, we would have seen something from this. So they are probably very weak. And the same goes for the hidden interactions. And there are bounds you can set on the hidden interactions. So they're also probably very weak. And this is, again, the Boole cluster picture I showed before. All right, so let me try to get back to this mass question. So what do we know about the lower bound? Well, for the lower bound, we can ask ourselves, well, how light can a dark matter be? And for this, we can look at to what structures are dark matter particles bound. And we know that it's always bound within galaxies. And the smallest galaxy will be about 1 kiloparsec. So the wavelength, the de Broglie wavelength of dark matter should not be larger than this 1 kiloparsec, because then the quantum effects will make sure that it cannot be bound anymore if the wavelength is larger. So we can just plug in orders of magnitude numbers, calculate the de Broglie wavelength. We know that the mass is light, so it will be at the speed of light. And we find the lower bound that it must be larger than 10⁻22 eV. Otherwise, we cannot bound it to galaxies. And it's pretty useless to account for our observations. Well, at least it will not be enough. The upper bound, on the other hand, comes from another idea. If we would have like a dark matter particle that's very massive and we would shoot it into a galaxy, then it will get close to some stars, and it will, due to its very massive, there will be gravitational interactions. So it will make sure that some of the stars will be tightly disrupted when this dark matter particle passes by. So we would expect to see some tidal disruptions when we observe galaxies or when we look at the CMB. And we haven't seen those. So that's how people got to 10 to the 70 eV. Okay, so then I would like to use quantum gravity now to say, can we try to narrow this window down a bit? And well, the first question is, if we ask ourselves, can we use quantum gravity? Then of course the first thing you would ask is, well, we have no theory of quantum gravity. So this must be very model dependent on the theory of quantum gravity that you like, that you work with. So we have to rephrase our question a bit and ask, can we make model independent predictions about dark matter from any theory of quantum gravity? And then there's two approaches you could take. Of course, the first approach would be to take some different models of quantum gravity, look at what are the similarities in these models, try to distill those, and try to predict from there. That's not the approach I would like to take today. What I would like to talk about is a more bottom-up approach. We have a theory of quantum gravity at very low energies. Can we try to predict something at higher energies? So in order to to go there, I would like to quickly recap why do we need a quantum gravity theory? What is the issue with quantum gravity? And of course, we all know it's not renormalizable as a quantum theory. And I will get back to that, but I think we first must ask ourselves, why do we actually want to embed quantum gravity into a theory of general relativity, into a quantum theory? And one of the questions I would like to be answered by a theory of quantum gravity is, how does general relativity, how does gravity work at high energies? So we know general relativity is a mathematically complete and consistent theory, but it does not really seem to account for all the physics. And we have recently, there was handed a Nobel Prize for Penrose for his fundamental work on showing that if you take a very simple, very natural assumptions, then you can form singularities. There's no way out of this. There will be singularities in our universe. Moreover, we have seen pictures of black holes recently. So there must be something like black holes. There are singularities, but there's a bit of an issue with singularities in general relativity. And that is, in order to form a singularity, you must collapse some kind of density profile to a delta distribution. And this is all fine if you work in the real space, where you can just take a Gaussian distribution, for example, and take the width to 0, and you end up with a delta distribution. On manifolds, this is actually very difficult to do, because during a process, you always need to satisfy the Einstein equations, and you want the metric to be smooth during the process. And it was shown in the 70s or 80s by Garog and Trashin that, in fact, you cannot really obtain a delta distribution by taking a limit of some distribution to 0 in a continuous way, such that your metric remains smooth during the process up to formation of the singularity. Of course, at the singularity, the metric is no longer smooth. So this is kind of an issue that I would like to see explained by a theory of quantum gravity. What happens at these singularities? And general relativity does not seem to provide a complete answer to this question. All right, so the way out for this would be to embed general relativity in a quantum theory, because we know our expectation is quantum deals with the small phenomena. Quantum theory tells us that we cannot really localize things. So here, embedding general relativity into a quantum theory seems to be a solution to this problem. And here we run into the problem of non-renormalizability, because the issue with quantum field theory is, although it's physically probably the best theory we have, considering the enormous amount of predictions from particle physics, for example, mathematically there are some issues with the theory in the form of divergences that we often end up with. Of course, we know how to deal with these divergences in ordinary quantum field theory. We can regularize and renormalize our theories. But for gravity, we just don't know how to do it. And this is the issue that we end up with. So let me try to explain this a bit. So the straightforward, the standard way people usually do this, or at least the first way people try this, is background field method. So we just start off with the action, the Einstein-Hilbert action, and we add, we can add matter to our action, but we want to quantize gravity. And we know that the field associated to gravity is the metric. So we'll split the metric in some background metric and some perturbation compared to the background metric. One can take Minkowski, that's the usual choice, but you can take any background metric. And we quantize this perturbation. And in fact, if we choose Minkowski, then we have a gravitational wave for H. So we have already observed the wave-like character of this perturbation. And all we want to know is, of course, the particle-like character, which we would call the graviton. So we can do this. But what we find is that if we do this and we get a non-renormalizable theory, So in order to make this work, we need to add r squared, r cubed, Ricci to the fourth, but we also need the Ricci tensor and all possible structures we can write. And we need an infinite amount of them. So the theory we end up with is no longer predictive. We need infinite amount of coupling constants that need to be measured, or at least Wilson coefficients. And this as a result has been known for a long time. And this is where the search for a theory of quantum gravity starts. So how can we get around this? What should we do to modify this? And there's many different approaches nowadays towards this question. And as I said, I would like to talk a bit about model-independent approaches. And the first thing we should observe is that the absence of UV complete theory, so this theory breaks down at high energies, does not mean that we cannot say anything at low energies. In fact, at zero energy, we know the theory of quantum gravity. It's just general relativity. But once we start to increase our energy, we have to add perturbations. And that's all fine. We can do perturbation theory for quantum gravity up to some scale where the perturbations are no longer convergent into a series, and we get a divergence. And this I will call the quantum scale of quantum gravity. So beyond the scale of quantum gravity, we can no longer do quantum perturbative. We can no longer, well, we can still calculate perturbative effects, but there's no use to it because the higher orders will be more important. And in fact, what I will talk about today is a bit also about the non-perturbative effects, because there's actually also some things we can estimate about non-perturbative effects at low energies. So the idea is we have an effective field theory of quantum gravity, which works up to some scale. And we can try to do predictions with it and try to compute things and see how far we get with this. And this is very similar to, for example, if you do Newtonian mechanics. Newtonian mechanics is not wrong, but we know at high velocities, at some point it breaks down and you need special relativity. Up to that point, we can still use an effective theory of Newtonian mechanics, which can give us predictions. All right. So then the question we need to ask is, what is the scale of quantum gravity? Where does quantum gravity break down? And the first thing you would do, at least I think most theorists would go for that, you just start with what are the constants in my theory? And we know we have a quantum theory, so there will be a h bar. There's gravity, so there's Newton's constant, and in fact, we also have special relativity, so there's C. We can try to form an energy scale. And here I just wrote down the reduced Planck mass. So this would be an order of magnitude, well, this would be a dimensional analysis of finding the scale where our effective field theory will break down. So up to this scale, one could expect that we find a theory of quantum gravity. But in order to set bounds on dark matter, we'll need to be a bit more specific than this. And fortunately, so yeah, the problem is we can always scale this with an arbitrary constant. So we still don't really have the information. Fortunately, there is some research, and one of the things people have looked at is if you look at the effective field theory of quantum gravity, then at some point you will violate unitarity at tree level. If you want to avoid that, and it was done in this paper by Han and Willenbrock, if you want to avoid that, then quantum gravity must, like the scale of quantum gravity must be smaller than the Planck mass. And then here's the number of scalars, fermions, and vectors you put into your theory. And if you would plug in the standard model in number of scalars, fermions, and vectors, then this would be around 1, this 160 pi divided by this number. So the scale of quantum gravity is expected to be, the upper bound for it is expected to be the Planck mass. And the lower bound, well, we know that we have not observed quantum gravity in experiments, not at LHC. So it must be at least larger, the scale of quantum gravity, than a few orders of magnitude beyond LHC scales. That's what we know. This upper bound is actually quite nice. So you might think that, well, this upper bound is not a very conservative thing, because that would the higher we choose the scale of quantum gravity, the larger the domain of our theory is. But for today, I'm just interested in testing our theory at scales that we can already test. And then I know that the scale of quantum gravity is not only like indicates the domain where effective field theory works, it also tells us how much suppressed quantum gravity effects must be. So the larger this quantum gravity scale, the more suppressed effects from quantum gravity that we could measure in current experiments are. So therefore, I will say that this upper bound is going to be a very conservative estimate for what the scale of quantum gravity is. All right, so this is what I'll assume the scale of quantum gravity is the Planck mass, and we're mostly interested in how much is the suppression of quantum gravity effects. All right, so what does this look like if we do quantum gravity? The first thing I said is very conservative. We can do perturbative quantum gravity. In perturbative quantum gravity, we will just look at the Einstein-Hilbert action, and we can add standard model physics. We could add the dark sector if we like, and we can start to integrate out our graviton. And in effective field theory, we just write down all possible operators that are respect the symmetries of our problem. And another way to look at this is these are generated by the loops of the graviton, so these counter terms. So these are basically the counter terms you would have to include. But we know that here we have 1 over g, this is order g to the power 0, this is order g. So the higher you go, the more suppressed they are until you reach the scale of quantum gravity, and then it's the other way around. So up to this scale, these corrections are very small compared to Einstein-Hilbert gravity. So we can actually do perturbative theory. Then there's two things to see here. First, there's local corrections to our Einstein-Hilbert theory. And these come from the UV divergences if we start to calculate the graviton loops in our theory. And the Wilson coefficients here are not really calculable from a low energy theory. So we would need a completion like string theory to calculate these Wilson coefficients. And that's because they come from the UV divergences. These guys, on the other hand, come from the infrared divergences in the loops. So these alpha and beta can be calculated model independently. There are numbers for this. I'm not showing them now because I want to go into the non-perturbative effects. But in principle, one can calculate this, and one can do this order by order, try to do perturbative quantum gravity. And then there can always be some additional boundary terms, which I've ignored here. So that's what one can do with perturbative quantum gravity, but there is an issue here if we want to talk about dark matter. So all this perturbative quantum gravity tells us is that if there is an interaction in our standard model Lagrangian, and there is an interaction in our dark matter Lagrangian, and we don't know anything about the interactions between the two, there will be interactions generated by quantum gravity, but these will be hugely suppressed. The best we can do is, well, we know that all the operators from the standard model times an operator from the dark matter Lagrangian will be there. They will, due to the fact that they all interact with via gravity, but it will be suppressed by the Planck mass to the power 4. And this is far beyond current experiments. The best we can do, I think, is probably go up to mp to the second, mp squared. I will talk a bit about that later. So unfortunately, perturbative quantum gravity cannot tell us much yet. What can we then do with non-perturbative? Yeah. So I don't think they have been calculated in loop quantum gravity. I'm not sure about it, but I don't think they got there. But I think in string theory, people should be able to calculate those. Also, I think in asymptotic safety scenarios, people should be able to put bounds on these coefficients for which you would get asymptotic safety. There are actually already some experimental bounds on these coefficients, but this is order 10 to the 70 something, I believe, from the top of my head. So these are very weak. This actually comes from the Iad-Wash experiment that I'll talk about a bit later. But yes, in principle, if we could measure these, then we could start to distinguish theory from gravity. Yeah, so this is not going to help us for dark matter yet. So what I want to talk about is non-perturbative quantum gravity. So I'm going to assume that we no longer have just ordinary virtual gravitons on our loops, but there might also be black holes in our loops. So we have to take a path integral over various geometries. There is some work done in this direction by Hawking and by Xu and by some other people, trying to estimate these effects. And all I will do today is make the argument that if we have an EFT, then in principle we expect all operators to be present that are that respect the symmetries of our problem. So in our case, the standard model symmetries, maybe other symmetries we put into dark sector, and of course diffeomorphism invariance. And the second thing we know is that if these operators exist, well, they must exist, so to say, in our EFT, or you must do something to get rid of them. But in a minimal extension, they will exist, and they must be suppressed by the scale of the physics that generates it. So they will be suppressed, in this case, by the Planck scale of quantum gravity. So what does it look like? We can write down interactions of some dimension. So it will be dimension 5 or larger in mass dimension. And there might be some interaction already between the standard model physics and dark sector. There might not be, but there will certainly be, by our arguments from EFT, will certainly be this interaction due to quantum gravity. And we know this scale from quantum gravity. We expect the Wilson coefficient to be 1 unless we do something extra to our theory. So we know that if there is this matter particle for some mass and we cannot measure something at the 1 over the Planck scale or 1 over Planck scale squared, then this particle cannot be there. Yeah, so this is the argument, and we see that at the Planck scale, this guy will always dominate over this guy. So unless the scale of suppression is smaller than the Planck scale, then we will first see the interactions between the dark sector and the standard model. All right, so that brings us into lower bounds on dark matter fields. So let us now just start playing the game. And what we can write down is we can write down our dark scalar field and try to construct operators of a certain dimension. In this case, we look at dimension 5, because dimension 5 will only be suppressed by the Planck scale. Dimension 6 will be suppressed by Planck scale squared, then Planck scale cubed, etc., etc. So the operators we can write down are the dark matter scalar coupled to the electromagnetic field or to a gluon. And then we can ask ourselves, do we have bounds on these interactions? So let us look at that. And we know for the bound, if we look at the electromagnetic interaction, there's quite strong bounds already. So we know the Planck scale is at 10⁻18, and we see that we don't see any particles in this range, right? Well, we just argued that we expect from quantum gravity that there must be, if there is a particle, scalar particle, then there must be some interaction here. We have not observed it. So that means that we can basically exclude this region for masses. So maybe the thing to first look at is what is this bound of the new forces? So there's this bound from new force. This is the famous Iad-Wash experiment. So what they do, they look for deviations from Newtonian potential. And if there would be some dark matter field, this would generate some Yukawa potential. And then they measure the coupling constant, which we expect to be 1. So we can look at alpha as 1 and then try to see which mass, well, they measure in the wavelength, but we can calculate the mass, see which mass it corresponds to. And that is the intersection that we found here. So what we see here, this line is basically the new forces line that we see in this plot. All right, so let us now try to draw this intersection. So we said, if we have this minimal extension and we don't do crazy things to our theory, then we expect an interaction here. We don't find anything. So we can basically exclude this part of the spectrum using this argument from quantum gravity, this basically order of magnitude argument. Of course, there is always ways out of such a bound. And the first would be to consider axions instead. And the thing we should ask about axions is, what are the symmetries if we include axions? So we know axions are odd parity. And the question is, does quantum gravity respect parity symmetry? And then there would be two answers we could give. We could say it should not respect parity symmetry. A reason could be there's arguments made that quantum gravity violates time reversal symmetry. So we would expect it to violate CP, probably also P. So we could accept that quantum gravity does not respect parity symmetry, and then we can just write down the same operators as we had before, and as I showed, we'll get the same bound. But of course, one might also argue that quantum gravity should respect parity symmetry, and then these operators are no longer allowed. They don't respect parity symmetry, so we would have to restore parity by considering these operators, where we look at the odd parity here. So what does it look like if we look at an axion? So in the first case, if it does not respect parity symmetry, we can draw the same line as we had before, because we knew from the new forces experiment that there cannot be any particles up to 10⁻³ eV. However, if quantum gravity would somehow respect parity symmetry, then we no longer have the earlier bound I showed. We no longer can use the new forces bound, and we have to get to our next best bound, which is here from the magnetometry experiments. Sorry about that. So then we go only up to 10⁻21 eV is our new bound. And this is actually very interesting, because there's lots of research now going on into these kind of magnetometry bounds. And actually, let me scroll back a bit. Same goes for the spectroscopy bounds. There's very nice experiments now being developed to look into that section. And if people can increase sensitivities of these experiments, then one could expect that this line will totally shift down a bit. So we could maybe expand this bound a bit in the future. But as we see, it's very important to think about which symmetry should be respected by quantum gravity and which not. All right. Then we can talk about other way out. So we can try to add something more to our dark sector. So we could, for example, charge our scalar field under a new local gauge interaction. And the consequence is, because standard model does not, is a scalar under this gauge transformation, we can no longer write down these operators. These are now charged. So we have to look at phi squared, f mu, and phi squared, g mu, because these are the only ones that satisfy the symmetries of our problem. And then we can start to ask ourselves, well, first we see it's now suppressed by np squared. What do we know about this? And well, actually, there are now some bounds in this direction. So we already get to 1 over np squared. But as we can see, we cannot really beat the bounds from, for example, galaxy formation yet. So these are bounds of the shape, of the type that if you have the dark matter density that we see today, and there's one component dark matter, then in order to form galaxies, dark matter must be more massive than 10⁻21. So although there is some perspective even on these interactions, we're not there yet. As we can, from quantum gravity, we can only get up to 10⁻22. All right. Then I think this is more or less the lower bounds I want to talk about. So yeah, this is the game you can play by just assuming what are the symmetries in our problem, what operators do we expect to generate, and what are the consequences, where do we expect to see interactions. So now I will quickly review some of the other bounds, go to fermions and vector particles, and also look at the upper bounds. So for fermions, we have the famous Tremaine-Gunn limit, that there's always a limited amount of fermions you can store into a galaxy. In the sense, we can take some Maxwellian distribution for the velocity, some isothermal distribution for the particles. Fermions cannot be in the same state. So there is a limited amount of fermions we can store into a galaxy. So in order to account for the dark matter we see, one can derive this bound of 10 to the 2 eV, which was derived by Tremaine and Gunn. And of course, if you're willing to take many more generations of fermions, you could, of course, loosen this bound a bit. But there are already quite strong lower bounds, so our approach is not really going to help to beat this bound. For vectors, there are no strong lower bounds known, except for the 10⁻22 I discussed at the beginning. But here again, our method is not really applicable here. We cannot write down the operators at dimension 5. There's no bounds that can increase this bound. And then the spin 2, in spin 2, we can always kind of follow the scalar particles. And the reason for this is that if the spin 2 is not traceless, then there will always be a scalar type interaction that you have to write down if you write down your spin 2 field. So those are the lower bounds on our fields. Then we can go into the upper bounds. And here there's already something known, and people have actually played a similar game as we played for the lower bounds here. What you can just write down the operator, expect a Wilson coefficient of 1. It's going to be Planck scale suppressed. And what could happen if this operator is present, then we expect that the dark matter field will decay into photons. So if we want a thermal production of dark matter in the early universe, and we want this dark matter still to be around today, then it should not have decayed too fast. So what we can do, we can estimate the decay rate into standard model particles and compare it to the age of the universe. And what we end up with is, if you just do this order of magnitude estimation, you would get this bound of 10 to the 7. If you would do it slightly more carefully, as was done by Mambrini, Profumo, and Farinado, then you can actually get slightly tighter bounds. But here I choose to just write down the order of magnitude estimate. And we can play a similar game for vector dark matter. So we can write a dimension 5 operator. So in this case, we look at a dark photon or a dark vector decaying into a graviton and a photon. We can write down this operator. We can estimate, we can make an order of magnitude estimate for the decay rate by calculating the amplitude. And we still see the dark matter, so it should not have decayed over the age of the universe. And again, we get up to like 10 to the 7 electron volt bound. Then for fermions, we can play a similar game. We can look at an operator we can write down. So we have a dark fermion decaying into a neutrino and a Z boson. And again, the same trick. You write down the decay rate compared to the age of the universe. And then we see that the fermion dark matter must be smaller or less than 10 to the 10 eV. So let us conclude from there. Using quite well-established arguments from quantum gravity, effective field theory. So we just write down minimal extensions. Suppose we have one additional field. What are the operators we can write down that respect the symmetries? Wilson coefficients are 1. They will be suppressed by the Planck scale. And then we can make order of magnitude estimates by comparing to the experiment on dark matter masses. So for scalars, we would find that scalar particles are somewhere between 10 minus 3 eV and 10 to the 7 eV. For axions, we had the same bound, unless quantum gravity respects parity symmetry, then we would shift this one back to 10 minus 22 or 10 minus 21. For fermions, we still have the Tremaine-Gunn limit. And for the upper bound, we use again the fact that dark matter will decay if these operators are present. For vectors, we do not get stronger bounds, so that's why our first paper was only about scalars and pseudoscalars. And again, the upper bound comes from the decay. And for the spin 2, we follow the scalars from the fact that we expect there to be a scalar interaction when we write down the spin 2 interactions. So that would lead to a bound between 10 minus 3 and 10 to the 7 EV. Yeah, so that's all the bounds you can write down. And I think this kind of reasoning could really help to plan future experiments and to see where dark matter could be found. And that was my talk. Thank you very much for your attention.
Thank you very much for Folkert for your nice seminar. This is quite interesting. We know that the majority of evidence for dark matter comes from gravity, so use that to constrain the dark matter particle is quite interesting. And I will open for questions now, and I would like to start with one. You are talking about a very light DM particle, right? And I was wondering if this can give problems, for example, to structure formation, because usually we have the standard, for example, WIMP scenario with warm and cold dark matter. And I know that you comment a little bit about this, but could you please comment a little bit more?
Yeah, so the structure formation, you mean, I guess the galaxy formation as well. And yeah, so, well, I mean, if dark matter gets too light and there's one type of dark matter, then, well, what I'm told from cosmologists is that we cannot, galaxies will never form, right? They cannot collapse into a galaxy.
Yes.
So we'll never get the structure.
Mm-hmm.
So that's why I think you could get a bit better than the 10 minus 22 EV mm-hmm. if you would follow these kind of bounds, yes.
But this particle can be hot or not?
No, we're talking about, well, I mean, cold dark matter in a sense where we can go up to mm-hmm. 10 minus 20.
Okay.
Yeah.
Okay.
But it's the weakly interacting light particles that that have been investigated quite a lot recently.
Yes.
And
Okay.
there's quite some experiments nowadays looking for this using time variation in atomic clocks.
Could you please comment a little bit about how the interaction of dark matter can affect the atom clocks? This is topics of your paper, right?
Yeah, so that's indeed the start. Well, you basically obtain a fifth force if you include a scalar particle. So that will lead to a time variation. We work in non-relativistic approximation. You get a time variation into your electromagnetic constant, for example. And this could be measured by clocks. Yeah, and actually, so they nowadays basically they look for these time variations up from like time variations from about like a few seconds, which would be here, up to a few years, which would be in this range of the spectrum. Yeah.
More questions for Folkert?
I do have one. I'm wondering whether you could also do for instance, spin 3/2.
Yeah, that's a good question. We simply haven't looked at that. I would have to think about that more. Yeah, we have basically focused on spin 0, half 1, and come up with the spin 2 because it probably contains a scalar. But you could play a similar game for spin 3/2. You just have to see which operators you can write down.
More questions?
I know the anthropic gravity scenario, but I don't know the details. But let me put it like this. These bounds apply if diffeomorphism invariance is respected by quantum gravity. So at the fundamental level. So I know there are quantum gravity models where diffeomorphism would be broken at like this quantum gravity scale. And the second thing you need is that quantum field theory, or in particular effective field theory, needs to remain applicable up to the Planck scale in that sense. So there are models of quantum gravity. I'm sure there are models that would not respect these bounds, but I think they're the minority. For example, string theory should respect these bounds.
I was wondering about that too low upper limit that you have. So that could exclude some WIMP scenarios?
Yeah, in principle, yes. The WIMP is, I think, usually around 1010.
Yeah.
So in principle, this would exclude the WIMP scenarios, yes. I have to say these are all order of magnitude.
We have for axioms.
Yeah, you expect some kind of similar
mechanism. All right.
Yeah.
And I have another question. It's possible to use quantum gravity also to put constraints on primordial black holes? I saw that you were applying these effective theories to black holes.
Yeah, that's something I would have to think about whether we can do that. We have looked at ordinary black holes using effective theory, but the effects are always like unmeasurable. I don't think I wouldn't see an easy way to put constraints on primordial black holes.
All right. More questions for Folkert? I have a question here from David. I'll try to translate here. There's a possibility that the dark matter can be an indicative that use a pseudo-Riemannian geometry could be an error. In your opinion, what's the chance that the problem is more geometric than connected to a Lagrangian of matter, for example?
Yeah, that's a good question. Let me think a few seconds about this one.
Okay.
Yes, no, I think in the end it is very much possible, and I would put that into what I said at the beginning, the category of maybe even something completely different. And I think actually entropic gravity was mentioned. I think that would also fall into the category of something completely different. Mm-hmm. Yeah, I don't know. I think it might very well be indeed that we have to go to a completely different theory. Maybe completely different geometry theory. That's something I would love to investigate at some point. But I think up to that point, until we find something reasonable for that, it's good to stick to the conventional methods and see what we can do. And I think that the majority of the dark matter community focuses on this fundamental particle scenario in the end.
Mm-hmm. So more questions? So I cannot see any more questions. So I think we can finish here. I would like to thank you again for the nice seminar. It was really good. And for accept the invitation and be here with us, share your research area with us. Thank you all for watching the seminar. And that's all. See you in the next seminar.
All right. Thank you, Folkert.
Very much. Yeah.
Bye.
Bye.